Hey guys, this is Miss Bufford, and in this video, we're going to talk about mole ratios and stoichiometric calculations. And so your learning goals are to be able to use dimensional analysis in your stoichiometric calculations. And so let's talk first about what stoichiometry is. Stoichiometry is the calculation of relative quantities of reactants and products in chemical reactions. And this idea or this method of calculating, the relative quantities of reactants and products is founded on the law of conservation of mass, where the total mass of our reactants is always going to equal the total mass of our products. And the reason it is like that is because remember that in a chemical reaction, we're not creating matter and we're not destroying matter. We're basically taking molecules and pulling those atoms apart and rearranging them into a new configuration to make a new substance. And so we end up with all of the atoms that we had started with just in a new arrangement. So our mass is going to be identical for our reactants and products. And remember that when we write out chemical equations to show what is happening in a chemical reaction, we have to balance those equations to make sure that we have the same numbers of each type of atom on either side, and we use those coefficients in that equation to show that we have the same numbers of atoms. All right, and so what this really means is that if we're given the quantity of one substance in a chemical reaction, then we can use stoichiometry, which uses the ratios from that balanced chemical reaction to calculate the quantity of any substance in that chemical reaction relative to the amount we started with, the amount of whatever substance it is that we started with. And so in order to perform these stoichiometric calculations, we have to use something called the mole ratio. And the mole ratio is basically what makes stoichiometry. And so this mole ratio is the ratio between the number of moles of any two substances in a chemical equation. And so far this semester, we've talked about, when we balanced equations, we talked about the fact that or when we have talked about balancing chemical equations, we've referred to these as just single molecules of whatever substance they are. So we've got one molecule of nitrogen and 3 molecules of hydrogen coming together to form 2 moles of ammonia. Well, two molecules of ammonia. But in the lab, it's not practical for scientists to think about what's happening with one molecule of this and one molecule of that, because chemists work with billions of particles at a time. And so when we talk about chemical reactions, we use we scale up and we use the term moles. And so in this case, that would mean that 1 mole of nitrogen is going to react with 3 moles of hydrogen to produce that 2 moles of ammonia. All right, so for the rest of the year, for the most part, we're going to be talking about these in terms of how many moles we have when we refer to the coefficients or the numbers in a balanced chemical equation. All right, so what a mole ratio is just a ratio that describes the mathematical relationship between two substances in a chemical reaction. For example, if we take a look at this first ratio here, in this chemical equation, and I'm using these coefficients, we'll just put a 1 here for right now. I'm using the coefficients as the numbers for my ratio. So I've got 1 mole of nitrogen here. So here's my 1 mole of nitrogen for every 3 moles of hydrogen that's required for this reaction. So my ratio between nitrogen and hydrogen here is 1 to 3. And when we use these ratios in a stoichiometric calculation, we write them as conversion factors. And we've learned about conversion factors before when we talked about how we can write an equivalence statement as a conversion factor. So remember, when we were talking about how, just for a simple example, we have 12 inches equals 1 foot. And we could write that as a conversion factor with 12 inches over 1 foot, or 1 foot, that's foot, over 12 inches. All right, so remember those conversion factors we wrote before, Now we're going to take that same idea and we're going to use these ratios here to write conversion factors that we are going to use as our mole ratios in our stoichiometric calculations. And what I want you to notice about these conversion factors is that the unit here is going to be the same on the top and the bottom. What is different is the substance that we have on the top and the bottom. And so this mole ratio is going to be the key for us converting from one substance to another substance in our calculations. All right, this is how we make that conversion. And so if you've ever traveled to a foreign country and you've had to exchange US currency for the currency of wherever you're going, you might be familiar with the term of exchange rate. And the exchange rate is what's used to calculate how many US dollars are equal to a certain number of, or a certain amount of currency in another country's currency. All right, so the mole ratio is kind of like the same thing in chemistry. It allows us to make the conversion from one substance to another, all right, because it tells us what the mathematical relationship between those two substances in that balanced equation is. All right, so with this in mind, let's go ahead and talk about some different types of stoichiometric calculations. And so what I've tried to do is I've tried to break this down into a format that you can kind of apply in, any different situation. So for example, if you have a problem that's giving you an amount of one substance in moles, and it's asking you to calculate the amount of the other substance in moles, that is called a mole-to-mole calculation. And that is the shortest, simplest form of stoichiometric calculation that you can do. All right, then we have one that's just a tad bit longer than that. We have a mole-to-mass calculation. And in this type of calculation, we are being given one amount in moles, and we are being asked to calculate the other substance in grams. All right, so we have to add an additional step to the end of that one. All right, and then the longest type of stoichiometric calculation that we're going to do is called the mass-to-mass calculation. And in your problem, it will give you an amount of one substance in a mass and ask you to calculate the amount of the other substance in a mass, or grams. All right, and so this is going to require an additional step on top of the mole to mass steps. All right, and so we're going to go through examples of each one of these and take a look at the steps that are going to be required to solve each of these. All right, and so when we set these up, you're going to have a basic framework for how you should set up every other problem that's asking you to go from moles to moles, or mass to mass, or moles to mass, right? The only one that I haven't really touched on here is about the same length as the mole to mass. It's just the opposite. So we're being given something in a mass and asked to calculate moles. And hopefully by the time we're done with these three, you'll understand how to do that. So let's go ahead and take a look at the first type, which is a mole-to-mole calculation. And remember, in this type of calculation, the problem gives us an amount of one substance in moles, and it's going to ask us to find an amount of the other substance in moles as well. All right, so the first step in any stoichiometric calculation is to double check and make sure that your chemical equation is balanced. You want to make sure that it's balanced properly, because if it's not balanced properly, then your mole ratios are going to be incorrect and you will not get the right answer. All right, and so then the second step is just going to be for us to use our mole ratio to make that conversion. So let's take a look at our first problem here. And this is a very simple problem. It says how many moles of oxygen gas can be produced from the decomposition of 5 moles of water. And now, although I did say this was a simple question, there's a tiny bit of fluff in here, and it's basically showing from the decomposition of 5 moles of water. Sometimes some of these problems are going to be loaded with lots of fluff that makes you feel like you've got to do something extra special to solve this problem. But the only thing that you really need to focus on is identifying what is being given to you and what you're being asked to find. All right, so I've double checked my equation here. I know it's balanced properly. And so what I want to do is I'm going to first look and see what is being given to me in the problem. And in this case, I'm being told that I have 5 moles of water. So that's going to be my given. And I'm going to write 5 moles underneath water in my balanced equation. So I'm kind of organizing this information here so it's clear for me to see where I'm starting and where I'm going. All right, and then I want to pick out what is being asked of me. So I'm being asked to calculate how many moles of oxygen gas, can be produced. And so I'm going to put my question mark under oxygen and write moles because it wants me to calculate that amount in moles. All right, so what this is telling me is that I'm going to start here at water and I'm going to go all the way to oxygen. Okay, so those are the only 2 substances that I have to worry about for this particular calculation. Okay, and so when I set up this stoichiometric calculation, it's going to look a lot like the dimensional analysis calculations that we did last semester where we're just multiplying a bunch of fractions, okay, or conversion factors. So I'm going to start with 5 moles. I have to start with what the problem gives me. And right now, with this simple problem like this, it might not seem like such a big deal, but when we're doing multiple stoichiometric calculations, all from the same chemical equation, things can get kind of confusing. And so it's really important that you include your units. In this case, we have moles here, and your label, which in this case would be the formula H2O. So always include your units and your labels in every number that you write in these calculations so that you don't get lost and forget what a number is and then feel like you have to start all over. All right, so there's my 5 moles of H2O. The next step here is going to be my mole ratio. So what I'm going to do, because I'm in moles, I can go ahead and set up my mole ratio. Is I'm going to go ahead and get that ready because remember, we're going to write our mole ratio as a conversion factor. And so let's go ahead and just write out the mole ratio as just a regular ratio, and then we'll write both conversion factors and we'll choose the right one. So I have 2 moles of H2O, all right, for every 1 mole of oxygen gas. And what I want to do is I'm going to write both possible conversion factors. I could have 2 moles of H2O over 1 mole of O2, or I could have 1 mole of O2 over 2 moles of H2O. All right, and the way that I know which conversion factor to choose is that it cancels out the substance that I don't want to end up in my final answer, and it gives me the one that I'm being asked about. So I want to choose the mole ratio that is going to allow me, in this case, to cancel out moles of H2O. All right, remember that units are going to cancel out just like numbers. And so remember in math class when you're dealing with fractions, if you're multiplying things and you have a 7 on top and a 7 in the denominator, they're going to cancel each other out. All right, and units, they do the same thing. So if I have moles of H2O on top and moles of H2O on bottom, they will cancel out. So I'm going to choose this second conversion factor here because moles of H2O is on the bottom. And I'm going to write 2 moles of H2O on the bottom and 1 mole of oxygen gas on top. All right, so now what I want to do is I want to plug this into my calculator. And the way that I'm going to plug this into my calculator is I'm going to type in the number that I started with. And the next fraction over, if I have a number that's anything other than 1, then I need to perform a calculation for that. And in this case, I just have a 2 on the bottom. And because 2 is on the bottom, I want to divide by 2. So I'm going to click the divided by button and then hit 2 and then hit enter. And so in my calculator, I should get 2.5 moles of O2. And my sig figs are off on here. Let's just pretend that I have a 5.0 here so that I can have 2 sig figs. All right, so there is my final answer. So that means if I start off with 5 moles of water, I will end up with 2.5 moles of oxygen gas. All right, so let's go ahead and take a look at the next type of stoichiometric calculation. And in this type, I have a mole to mass calculation. So I'm starting with moles and I want to end up with the other substance in a mass, okay? And so remember step 1, we're going to balance our chemical equation. Step 2 is going to be to use our mole ratio to convert from moles of one substance to moles of the other substance. And then the last step here is to use our molar mass to convert from moles to grams. All right, so let's go ahead and take a look at our example. So again, this is, the same problem, only this time I'm being asked to calculate grams of oxygen instead of moles of oxygen. So again, the first things I want to do is I want to pull out the information that's being given to me. I'm being told that I have 5 moles of water again. So I have 5 moles of H2O. And this time I am being asked about oxygen still, but now I need to give my answer in grams instead of moles. All right, so I'm going to go ahead and start my calculation with what's given to me. So I have 5 moles of H2O. And then since I'm in moles, I can go ahead and use my mole ratio. That's step 2 here. So I'm going to set up my mole ratio. And I know that my ratio here is 2 moles of H2O to 1 mole of O2. And now that we're kind of hopefully starting to get the hang of writing these mole ratios, let's go ahead and just, instead of writing both of our possible conversion factors out here, let's just go ahead and see if we can decide where they go. So remember, I want moles of water to cancel out. So I'm going to take this and I'm going to put it on the bottom of my mole ratio. All right, and that means I have to put this one on top. So 1 mole of O2. One other way to remember where you need to put each thing in your mole ratio is that the moles of the substance that you start with always go on the bottom because you're always going to want to cancel those out. And the moles of the substance that you're trying to calculate are always going to go on the top because that's what you want to end up with, right? So in this case, if we take a look, our moles of H2O will cancel out. And now I'm in moles of oxygen. But the problem wants me to calculate grams of oxygen. So I have to do one more additional step. And that is that I need to convert from moles of oxygen to grams of oxygen. And I do that by multiplying by my molar mass. All right, so the molar mass for O2, if I have oxygen, there's 2 of them. I multiply that by the molar mass here, and I get 32.00 grams per mole. All right, so there's my molar mass for oxygen. So 32.00 grams of O2 for every 1 mole of O2. All right, now I can plug this into my calculator. And in my calculator, I'm going to type 5, because that's what I started with. And then in my mole ratio here, I've got a 2 on the bottom, so I'm going to divide by 2. And then in my next fraction over this molar mass, I've got 32 on top. So that means since it's on top, I'm going to multiply by 32. And if I plug this all into my calculator, I end up with 80 grams of O2. All right, so there's my final answer for this one. And remember that for the rest of this year, if we're doing stoichiometric calculations, to keep things simple, just match up your significant digits with the number that you start with. Right? In most cases, that's actually going to be the number that's determining our sig figs. But there are some other cases where your significant digits might potentially be limited by your molar masses. Just don't worry about that. Always match it up to the number that you start with. And in this case, we have 1 significant digit here, and so we need 1 in our final answer. All right, so let's go ahead and take a look at the longest type of stoichiometric calculation, and this is our mass-to-mass calculations. And remember, in this type of calculation, I'm being given my initial substance in mass, and I'm being asked to calculate the other substance in a mass as well. All right, so this is going to add an additional step. So Again, step 1, make sure our chemical equation is balanced. Step 2, we want to determine the number of moles of our given substance by using our molar mass. And so we have to first convert from grams to moles. We cannot use our mole ratio if we are in grams. We have to convert to moles first. Then we will set up our mole ratio, and then we will convert from moles to grams again. We'll convert back to grams. All right, so let's take a look at this problem. This is a similar problem, but this time I'm being told that I have 100 grams of water. So how many grams of oxygen gas can be produced from the decomposition of 100.0 grams of water? All right, so let's go ahead and pull out the information we're being given. I'm being given 100 grams of water. All right, so there's my 100 grams of water. And then it's asking me to calculate an amount for oxygen in grams as well. So I'm going to start this problem with what's given to me. All right, so I know that I have 100.0 grams of H2O. All right, and I can't set up my mole ratio just yet, because if I put my mole ratio in here, moles and grams are not going to allow each other to cancel out. And I really need water to cancel out. I need to get rid of water. So in order to use my mole ratio, I first have to convert from grams to moles. All right, so I'm going to do a conversion first, and I'm going to divide by the molar mass. And the molar mass for water is 18.02 grams per mole. Grams of H2O per mole of H2O. All right. So this is going to allow me to cancel out grams of H2O, and now I'm in moles of H2O, and now that I'm in moles, I can use my mole ratio. All right, so now I can set up my mole ratio, and remember the ratio between water and oxygen here is 2 to 1. And so remember that when we write our mole ratios, those numbers come from these coefficients in this balanced chemical equation. All right, so I'm not even going to write the ratio out this time. I'm going to pull those numbers down from my chemical equation, and I'm going to say I know I have water here, so I'm going to have 2 moles of H2O on the bottom. And remember, I'm getting that number from this right here. And then I have 1 mole of oxygen gas. And remember, I'm getting that number from right here. And there's my mole ratio. And what this is going to allow me to do now is cancel out moles of water. And now I am in moles of oxygen. So now I'm dealing with an amount of oxygen. Okay? But the problem wants my final answer in grams. And so I'm going to have to do one more additional step here. And I'm going to have to convert from moles of oxygen to grams of oxygen. And I do that by multiplying by the molar mass for oxygen, because now I'm in oxygen. So 1 mole of O2 is equal to 32.00 grams of O2. Okay, and now you'll see that my moles of oxygen will cancel out, and I'm left with my final units of grams of oxygen. All right, and then I need to perform this calculation. So in my calculator, what I'm going to do is I'm going to type 100 divided by 18.02, because 18.02 is in the denominator of that next fraction. And then I'm going to look at the next fraction over, and I have a number 2 there, so I'm going to hit divided by again, and I'm going to type in 2. And then in my next one over, my last one there, I have 32 on top, so I'm going to multiply by 32 because that's on the top. And then I'm going to hit enter. So let's go ahead and plug this in really quick. So I've got 100. Sorry, my calculator is not cooperating. Here we go. 100 divided by 18.02. divided by 2 multiplied by 32. And I get my calculator answer of 88.79023, and then some more digits, but that's plenty. All right, so now I need to make sure that my answer is in the correct number of significant digits. And I started this problem with 4 significant digits, so I need to have 4 in my final answer. So I'm going to start counting from the first non-zero digit. So 1, 2, 3, 4. And that means that 9 right here, that's my last significant place value. And since the next one over is 0, I am not going to round that 9 up. And I end up with an answer, a final answer of 88.79 grams of O2. And there is my final answer. All right. So hopefully this video was helpful. Please let me know if you guys have any other questions about this, and I will see you in class. Thanks for watching Buffered Chemistry. Subscribe to my YouTube channel for more chemistry help.